Welcome to the deep dive. Today, we're embarking on a journey, really looking beyond just the blueprints and the building sites.
Hmm.
We want to explore that incredible tapestry, of human ingenuity that shapes the very world we actually live in.
Right.
We're going to try and understand how we design things, how we engineer them, and crucially, how we manage the creation and maintenance of our physical surroundings. Everything from, the grandest ancient structures right up to the complex systems in a modern smart city.
And for this deep dive, we've pulled together a really rich collection of sources. It's quite a mix, actually.
Okay.
Everything from ancient architectural philosophy, Vitruvius and the like,
Yeah.
to cutting-edge research on digital project management, things like BIM.
Right.
And these sources, taken together, they reveal this fascinating interconnected story. It's a real chance, I think, to understand the why and the how well, behind both the permanence and sometimes the surprising impermanence of our built world.
That's a good point.
And hopefully uncover some of those vital, often hidden connections that make it all work, or sometimes why it doesn't quite work as planned.
Yeah, absolutely.
Hmm.
So, our mission today is really to distill the most important nuggets of knowledge, the key insights into this incredibly multifaceted process of building and maintaining everything around us.
Hmm.
We want to offer you, the listener, a shortcut, if you will, to being genuinely well informed about the complex forces that are always at play.
Yeah, let's get into it.
Okay, let's dive in.
Yeah.
So, to really understand where we are today with building, we have to look back, don't we? How far back do these fundamental ideas about construction, about design, actually go? Our sources hint at some incredibly early and frankly sophisticated concepts that really laid the groundwork for everything that came after.
It's quite remarkable when you dig into it, isn't it? What's truly fascinating, I think, is how the very first principles of architecture weren't just about shelter. They were deeply interwoven with the culture's beliefs, its rituals, and crucially, with the direct properties of the local materials they had access to. You couldn't just order steel beams from anywhere.
Of course.
So if we connect this to the bigger picture, it's really about understanding how these early civilizations adapted to their specific environments and resources, not just to build, but to create these enduring forms that were, in effect, profound statements about their values, their power, their view of the cosmos even.
Statements. I like that. It captures it perfectly. And when you look at something like the Egyptian mastery that our sources describe, Kostov talks about this quite a bit, you genuinely see that architectural statement carved in stone.
Oh, definitely.
He highlights this superb geometry and clean abstraction you find in places like the Valley Temple next to Chephrons Pyramid. It wasn't just about being big, it was about this almost otherworldly precision.
Mm-hmm.
Those square uprights and lintels, the walls having that pronounced batter, that slight inward slope.
Yeah, it gives it that solid look.
Exactly, makes them feel so much more stable and imposing. And the materials, using things like red granite from Aswan.
Which had to be transported huge distances.
Incredible effort. So it wasn't just construction, it felt like an art of pure monumental form, chosen for its beauty, yes, but also its incredible durability. It was all about signifying permanence, eternity.
Precisely. And that sense of deliberate, almost sacred construction. It really stands in contrast when you then turn to Roman pragmatism.
Okay, yeah. How did they differ?
Well, Viollet-le-Duc, for instance, suggests that Roman architecture was often driven more by necessity
Right.
and unvarying policy, basically the practical demands of running a vast empire.
Infrastructure.
Exactly. Less about what he called conviction, which maybe implies the more aesthetic or spiritual motivation we saw in Egypt. The Romans were master builders of infrastructure for conquest, for administration.
So function over form, maybe?
To a large extent, yes. Their reliance on masses of rubble faced with stone, marble, or stucco was ingenious in its own way. It allowed for incredibly rapid and extensive construction across a huge territory.
Ah, okay. So the facing provided the look, but the core was quick and cheap.
Pretty much. Palladio even gives details on how their brick walls were often built. Square bricks on both sides, and the middle filled up with cement and pounded bricks. And then they'd use larger brick courses every so often to bind it all together.
Very practical.
Extremely practical. This was efficient construction on an unprecedented scale, really aimed at function and empire building, maybe less focused on purely aesthetic ideals compared to, say, the Greeks.
Okay, so that brings us to the Greek aesthetic. How did that contrast with the Romans? Because we often lump Greco-Roman together, but they sound quite different in approach.
They were very different in their structural philosophy, certainly in the classical period. For the Greeks, the visible form was the structure. It was everything. Viollet-le-Duc describes how they emphasized structures where the superimposed architectural orders, Doric, Ionic, Corinthian, like you see in the Temple of Neptune at Paestum, formed a perfect connection, a harmonious whole.
So no hidden rubble course.
Generally, no. It was about the intrinsic beauty and the harmonious relationship of every single visible element. Le Corbusier, much later, of course, captured this perfectly when he pointed to the Parthenon as an example of pure forms and precise relationships,
Right.
reflecting deep mathematical speculation. Their buildings were almost physical manifestations of philosophical ideals, balance, proportion, harmony,
It sounds much more considered, maybe, less purely practical than the Romans.
considered and also codified. These ideals, especially the pursuit of harmony and correctness, were meticulously detailed. You see this brilliantly in the Vitruvian Principles.
Ah, Vitruvius. Everyone quotes Vitruvius.
And for good reason. His writings, later interpreted and hugely popularized by figures like Palladio, laid out precise proportions for everything. Architraves, friezes, the little decorative bits called cymatiae.
Wow.
What's really insightful is his categorization of temple types based on their intercolumniations. That's the precise spacing between the columns.
Okay.
He wouldn't just say space them out nicely. He'd identify specific types. Pupna style for closely spaced columns, giving a dense, strong look. Systyle, diastyle, area style for wider spacing. And then U-style as the ideal, most harmonious spacing.
That's incredibly specific.
It is. It gave architects a clear, systematic framework to achieve what was considered perfect design. And it was intended to be replicated and understood across the Roman world, and as it turned out, for centuries beyond. This systematic approach really speaks volumes about their ambition to formalize and disseminate architectural knowledge.
Okay, so the ancients gave us these really distinct approaches: philosophical, pragmatic, aesthetic. But what happened when the context changed dramatically? After the fall of the Western Roman Empire, when those vast resources just weren't there anymore, and new societies with new needs started to emerge.
Right.
How did builders in the Middle Ages adapt? They faced new constraints, different liturgical requirements for churches. How did they forge entirely new structural paths?
That's a fantastic question because this period, the Middle Ages, truly marks a pivot. It's a fascinating case study in innovation under pressure. What you see is builders having to reconcile their ambitions. They still wanted to build impressive structures, especially churches, but with suddenly limited technology and materials compared to Rome.
So necessity became the mother of invention.
Absolutely. The functional reason for architectural choices really comes to the forefront in this era. It was driven by resource scarcity, yes, but also by the evolving needs of the church, the liturgy. It was an incredibly ingenious response to a completely new set of circumstances, forcing innovation out of necessity.
And our sources point to these early medieval departures from classical norms almost immediately, right? Kostoff mentions a disregard for classical unities and these sort of fragmented interiors in early churches like San Pedro de la Nave in Spain.
Mm-hmm.
And the key point is, this wasn't because they lacked skill or forgot the old rules. It reflected a specific functional reason for dividing up the space.
Exactly. You had an increasing separation of the clergy from the faithful in liturgical practice.
Ah.
And the interiors needed to accommodate very specific, often multi-stage rituals. So they deliberately broke up those grand, unified, open spaces you saw in Roman basilicas. It's a clear example of how profoundly social and religious shifts could directly shape the physical design of buildings, especially sacred spaces.
That makes sense. And structurally, they couldn't just replicate Roman methods anyway, could they? Without the immense resources Rome had commanded.
Precisely. That lack of resources forced an abandonment of those huge, sprawling Roman ground plans, and it led to one of the most crucial innovations of the era, vaulting and support systems.
Replacing timber roofs.
Yes. Timber roofs were common earlier, but they were a constant fire risk, especially with candles and incense burners inside churches.
That's a good point.
Plus, they were vulnerable to damp and variable climates in Northern Europe. So builders turned to more durable stone vaulting. But
There's always a but.
there's always a structural but. Stone vaults are heavy, and they exert a significant outward thrust on the walls. They want to push the walls outwards.
Right. So how did they stop the buildings from collapsing?
Well, the earliest solutions were brute force.
Mm.
Just make the walls incredibly thick.
Yeah.
but that was hugely expensive in terms of materials and labor, and it made for rather dark interiors.
Okay.
So the real evolution began. First, distributing that outward thrust on the specific points using groined vaulting, where two barrel vaults intersect. Then strengthening those specific points with robust internal piers. And finally, the big breakthrough, counteracting the remaining lateral forces with external supports, the buttresses, often weighted down on top. Viollet-le-Duc describes this brilliantly, how stability was achieved by heavily weighting these external supports. It was radical, effectively supporting the building by means of points of support independent, as it were, of the building itself. The support structure moved outside the main walls.
And that whole line of development, that structural logic, led directly to the Gothic Revolution, didn't it?
Absolutely. It culminated in Gothic. And
Yeah.
Viollet-le-Duc frames Gothic architecture not just as a style, but almost as a philosophical stance. He called it a protest against monastic influence, and the first and most vigorous reaction of knowledge, examination, and inquiry into facts against tradition.
Wow, that's a strong claim.
It is. He saw it as incredibly rational and dynamic. It developed with incredible rapidity, achieving a kind of perfection of practical appliances, almost like a structural formula for building tall and light-filled spaces.
And it wasn't anonymous work either, was it? Gimple points out something really interesting. The practice of actually inscribing the names of the master builders, the men of genius like Robert de Luzars at Chartres Cathedral.
Yes, that directly challenges the romantic myth of the anonymous medieval craftsman toiling away solely for the glory of God. These were celebrated engineers and artists, recognized in their time for their groundbreaking contributions.
That's fascinating. It really changes how you picture that era.
It does, and the very structure of Gothic cathedrals, with their soaring vaults and that intricate, visible skeleton of buttressing, almost made the building's internal forces explicit. It celebrated the engineering itself.
Yeah, you could almost see the lines of force.
Exactly. And this era also truly highlighted the critical importance of material selection. They didn't have standardized materials catalogs. Builders had this profound, almost intimate knowledge of their local stone.
Right, they used what was available nearby.
Precisely. Clifton Taylor gives examples like the Chilmark and Tisbury oolites from Wiltshire in England, or the enduring preference, even today, for Clipsham stone in cathedral restorations in new buildings in places like Oxford.
So the stone itself dictated possibilities?
Absolutely. The specific properties of these stones, their strength, how easily they could be carved, their appearance, how they weathered, dictated what was structurally possible, and frankly, how long the structure would last. It was a truly regional art form, deeply, deeply tied to the local geology.
Okay, so we've seen these incredible innovations emerge, driven by both high-minded philosophy in the ancient world and stark necessity in the medieval period. What happens next, though? We get to the Renaissance. Did they just hit copy-paste on the ancient forms? Or was there something new happening, a reinterpretation that led to entirely different architectural expressions?
That's the perennial question, isn't it? It feels like this constant conversation across the centuries, a push and pull between respecting history and driving innovation. And you're right, the Renaissance wasn't just copying. What's fascinating is this continuous dialogue between those rediscovered past forms and, importantly, new structural capabilities or different material realities. The Renaissance certainly wrestled with classical ideals, reinterpreting them through a new, maybe more scholarly lens,
Okay.
while later movements like modernism took a far more radical approach, fundamentally redefining space and materials, but often still searching for their own versions of unity, grandeur, and economy. It's a testament to how architectural thinking keeps evolving, building on the past, but also making bold leaps forward.
And when we talk about that Renaissance reinterpretation, you almost have to start with Andrea Palladio, don't you? Our sources bring him up again.
He's unavoidable, and rightly so.
He seems key. They note that despite often using, maybe surprisingly, cheap material like brick faced with stucco instead of solid stone, he created these incredibly influential works. The Villa Capra, the Teatro Olimpico.
Iconic building.
Absolutely. He wasn't just slavishly copying Roman temples, he was adapting them, translating that classical grandeur into new contexts like country villas or theaters, and skillfully utilizing the materials available. His pattern book spread his ideas far and wide, shaping the look of neoclassical architecture for centuries, right across Europe and into America. His influences just Immense.
Immense. And moving further forward in time, you see another kind of brilliant synthesis in Wren's eclectic genius.
Christopher Wren after the Great Fire of London.
Exactly. Kostoff describes his work, especially the London churches, as a masterful blend of different sensibilities, medieval, classical, Baroque. He didn't rigidly stick to one style.
No, he mixed them up.
Skillfully, yes. He integrated different elements into a cohesive style that was distinctly his own, yet felt harmonious and universally admired. His work really shows an unparalleled understanding of architectural history combined with this incredibly innovative spirit. He was a true master of adaptation and creative integration.
Then, if we jump across the Atlantic, we see a different kind of giant in Frank Lloyd Wright's evolution. Ah, right. Banham makes this interesting point that the first Mr. Wright and the last were different kinds of architects. He evolved so much.
He really did.
From those early, horizontally focused prairie houses and Unity Temple to later very different masterpieces like the Larkin Building. He cemented his reputation as arguably America's greatest architect to date, and certainly a world-renowned domestic architect.
And his influence went beyond the U.S. border, too.
Significantly, Kostoff and Wright's own autobiography mention his significant influence on Europe's avant-garde after about 1910, particularly in Germany, Scandinavia, Finland. He was this force of nature, constantly pushing boundaries, exploring new forms, and fundamentally redefining what American architecture could be.
And that leads us almost inevitably towards the truly radical shift with modernism and figures like Le Corbusier's vision for the future.
Le Corbusier, yeah. Polarizing figure, but undeniably influential.
Hugely influential. He championed revolutionary ideas like his plans for cities with streets with setbacks, creating vast, airy, and sunlit spaces, and buildings with simple facades with immense bays, the ribbon windows.
Very different from traditional cities.
Completely. He famously viewed the architect as, above all, an engineer, emphasizing the importance of straight-line, square set as the grand acquisition of modern architecture.
So, rationality and engineering first.
That was the idea. He believed modernist architecture should be anti-monumental, rejecting traditional notions of permanence. He even compared a building to a tool, saying the motor car is becoming a tool. It was this complete reevaluation of architecture's purpose, trying to create efficient, functional, adaptable environments for a new mechanized age, machine age aesthetics.
Okay, so we've traced this amazing journey through architectural history, looking at styles, philosophies, but now let's shift gears a bit and really dive into the science behind it all. Beyond the aesthetics, our sources get deep into the very stuff buildings are made of.
The materials themselves.
Exactly, and how they're engineered to actually stand up, against gravity, against wind, earthquakes, the ravages of time. It's the invisible strength, the real backbone of all construction.
That's right. And this brings up a really important question. How do engineers and builders ensure structural adequacy and, just as importantly, longevity, especially when facing both static loads, just the weight of the building and its contents, and dynamic loads like wind or seismic activity?
Yeah, the forces involved are immense.
They are. So if we connect this to the bigger picture, it's all about understanding the inherent properties of different materials, what they're good at, what their weaknesses are, and constantly innovating to meet ever greater demands for height, for longer spans, for better durability. Every material, whether it's ancient stone or a modern composite, has its own unique story, its strengths, and its limitations.
And of course, one of the oldest and most fundamental is the treeness of wood. It's been with us forever.
Right from the start.
Kidder talks about the fundamental strength of wood, explaining how its fibers are incredibly strong in both compression and in tension, and how proper framing in a house actually reproduces treeness. It uses that natural strength effectively to resist all those forces.
It's a beautiful concept, reproducing treeness.
Isn't it? And Hoadley gets even more specific, discussing fascinating differences like ring-porous woods, think oak and ash with those visible rings of large vessels versus diffuse-porous woods where the structure is more uniform.
Okay.
And he highlights the critical impact of things like equilibrium moisture content, how much water the wood holds in balance with the air and the fiber saturation point.
Okay.
These affect how wood moves, shrinks, swells.
Which is hugely important for stability.
Absolutely. Understanding wood isn't just basic carpentry. It's like understanding organic, natural engineering right down to the cellular level.
It really is. And then building on those natural foundations, you have the enduring strength of masonry and concrete.
The heavyweight.
Literally. Our sources detail the impressive crushing strength of materials like Portland cement mortar or ashlar granite. These materials have formed the bedrock of construction for millennia, offering incredible resistance when squeezed compressive strength.
Right.
But innovation hasn't stopped there. Today, we're seeing incredibly sophisticated precast, pre-stressed concrete structural elements.
Okay, what does prestressed mean exactly?
It means high-strength steel cables are stretched inside the concrete form before the concrete is poured. Once the concrete hardens, the cables are released and they compress the concrete, essentially giving it a built-in resistance to bend in forces.
Oh, clever.
Very clever. Fundamentals of building construction mentions things like wall panels with built-in concrete studs that can span multiple stories. This allows for faster, more efficient assembly of incredibly robust structures, leveraging concrete's inherent compressive strength in new, more versatile ways.
And then for really tall buildings, for the modern cityscape, we absolutely have to talk about steel, the backbone of the modern city.
Couldn't have skyscrapers without it.
Exactly. Steel gave us the ability to go truly high-rise, but it comes with its own unique set of engineering challenges, doesn't it?
It certainly does. A critical one is fire resistance.
Right, steel melts or warps in fire.
Well, it doesn't melt at typical building fire temperatures, but it loses its strength very rapidly when heated. So protecting it is crucial. Building Codes Illustrated and Kidder Parker highlight how this is achieved, usually through poured concrete encasement, basically wrapping the steel beams and columns in concrete, or by spraying them with sprayed fire-resistant materials, often called SFRM.
That fluffy stuff you sometimes see.
Exactly. It looks a bit like cottage cheese sometimes. These are absolutely essential because unprotected steel can fail very quickly in a fire.
So the engineering is precise.
Incredibly precise. Engineers rely on detailed calculations, consulting complex tables for things like beam connections, web shear, how much force the vertical part of a beam can take, and allowable end reaction, how much load a beam can transfer to its support. Every single piece has to be calculated to handle its specific load safely, with significant safety factors built in.
It's amazing it all holds together.
It is. And that brings us to the evolution of materials as a broader concept. It's not just about using traditional materials like wood and stone, or inventing entirely new ones like plastics or advanced alloys. It's also about constantly finding new ways to combine and optimize them.
Like composites.
Exactly. Hoadley discusses composite panels, you think plywood, OSB-oriented strand board, particle board. These leverage different wood elements, everything from thin wafers of wood aligned in specific directions, down to literal sawdust, all bonded together with resins.
So using more of the tree.
Precisely. It maximizes resource use, minimizes waste, and creates engineered wood products with specific, tailored properties for different applications. Strength in one direction, stability, cost-effectiveness. It's a fantastic example of how engineers are continuously pushing the boundaries, making materials perform in ways never before imagined, often by combining them intelligently.
Okay, so we've got the structure sorted, the building can stand up, but here's where things get really interesting for day-to-day life inside the building. It's not just about survival, it's about how the building interacts with its environment.
The climate, the sun, the air.
Exactly. And how it performs for the people inside, often silently, efficiently. This goes way beyond just basic shelter. We're talking comfort, health, energy use, ecological responsibility.
Yeah, the building skin or envelope is incredibly important. What's fascinating here is the holistic view that's really taken hold in modern construction, heavily driven by the need for sustainability.
Right, green building.
Green building, high-performance building. If you connect it to the bigger picture, it's all about minimizing environmental impact across the building's entire life, optimizing energy use, and maximizing the well-being of the inhabitants. The building isn't just a static object anymore. It's seen as an active participant in its surrounding ecosystem, constantly mediating between the inside and the outside conditions.
And a huge part of that mediation is thermal regulation, right?
Yep.
Keeping warm in winter, cool in summer.
Absolutely fundamental. Fundamentals of residential construction makes the point that a ceiling requires more insulation than a wall.
Why is that? Heat rises.
Heat rises, yes, but also think about solar gain. The sun beats down directly on the roof, much more intensely for longer periods than on vertical walls, especially in summer.
Oh, okay, that makes sense.
So you need more R value up there. And in cold climates, as building science guru Joel Sturbrook always emphasizes, strategies include careful placement of vapor retarders and air barriers. Usually these go on the interior warm side of the insulation.
To stop moisture getting into the walls?
Exactly. To prevent warm, moist indoor air from condensing inside the cold wall cavity, which can lead to mold and rot. and the air barrier stops heat loss through uncontrolled air leakage drafts. These seemingly small details have massive impacts on energy efficiency, durability, and occupant comfort.
And windows used to be terrible for heat loss, didn't they? Single panes of glass.
Huge energy drains. But windows have undergone a complete revolution. Advanced glazing technologies are incredibly sophisticated now.
Like double or triple glazing.
Yes, but much more than that. Sustainable construction details how modern windows, double glazed or even triple glazed, often have invisible low-E coatings, standing for low emissivity. These coatings reflect heat radiation, keeping heat inside in winter and outside in summer.
Wow.
And the spaces between the panes are often filled with inert gases like argon gas, which insulates better than air. Windows are now engineered with very specific solar heat gain coefficients, SHGC, how much solar heat they let through, and visible transmittance, how much light gets through.
So you can tune the window for the climate.
Precisely. You might want high SHGC in a cold climate to capture winter sun, but low SHGC in a hot climate to keep solar heat out. We even see aesthetic innovations like butt joint glazing, mentioned in Fundamentals of Building Construction. This uses structural silicone to join large panes of glass with minimal visible framing, creating that strong effect of unbroken horizontal bands of glass. High performance meets sleek, modern looks.
This constant push for efficiency and lower impact really comes together in the rise of sustainable construction, doesn't it?
It absolutely does. We're seeing major movements in certification systems like LEED leadership in energy and environmental design and green globes, setting increasingly high benchmarks for building performance.
Right. You see those LEED plaques on buildings now.
You do. And sustainable construction highlights the focus shifting towards life cycle assessment, LCA. That means considering the environmental impacts of a building from the very beginning, extracting raw materials through manufacturing, transportation, construction, operation, maintenance, and all the way to eventual demolition and disposal.
Thinking about the whole lifespan.
The entire lifespan. And setting ambitious energy consumption targets, especially for things like high-performance office buildings, this isn't just about piling on more insulation. It involves truly integrated design strategies. Things like careful building orientation to optimize solar gain and daylighting, designing for natural ventilation, using daylight sensors to automatically dim or turn off artificial lights when there's enough natural light, and installing super high-efficiency HVAC systems. It's a comprehensive, systems-based approach.
And that environmental focus extends right inside the building, too, with indoor environmental quality, IEQ.
Yes, and this is hugely important. IEQ isn't just a buzzword. It directly addresses the health of the building occupants.
So air quality.
Air quality. Indoor air quality, or IAQ, is a big part of it, yes. But IEQ also covers things like noise and lighting quality. Are the acoustics good? Is the lighting comfortable and appropriate for the tasks? Our sources point to the development and use of new building products with zero or low emissions of VOCs, volatile organic compounds, which can off-gas from paints, carpets, furniture, and affect health. And they stress the critical importance of proper sizing of HVAC equipment. Oversized air conditioning, for example, might cool quickly, but not run long enough to remove humidity effectively.
Leading to dampness.
Exactly. And that necessitates careful humidity control to prevent issues like mold and mildew, which are major health concerns. It's all about creating indoor spaces that are not just safe and energy efficient, but actively contribute to our well-being, our comfort, and our productivity. We spend so much time indoors, the quality of that environment really matters.
Okay, so we have this incredibly complex science, evolving design philosophies, advanced materials, but holding it all together, making sure it's safe and functional, is this invisible framework of rules and regulations, building codes.
The rule book.
How do these ensure safety, and how do they make sure buildings are actually usable by everyone? These codes are easy to just take for granted, but they must be incredibly complex and absolutely vital.
They are incredibly complex and absolutely vital. That's a crucial point. If we connect this to the bigger picture, building codes really represent a dynamic societal consensus on minimum safety standards. They're not dreamed up arbitrarily.
No, they come from experience.
Exactly. Often painful experience learning from fires, collapses, earthquakes. And alongside safety, you have accessibility standards, like the Americans with Disabilities Act, ADA, in the U.S., which reflect our evolving societal values about equity and inclusion in the built environment. They're not static documents. They're constantly being updated based on new knowledge, new technologies, and societal expectations, all aimed at protecting us and ensuring buildings truly serve everyone.
And a huge chunk of these codes is dedicated to pure engineering requirements, isn't it? The structural stuff.
A very significant portion, yes. Building Codes Illustrated explains how these mandates cover everything from static loading, that's the predictable permanent weight of the building itself, plus occupants, furniture, equipment, to dynamic loading.
Things that move or change.
Right. Unpredictable forces like earthquakes, heavy snow loads, strong wind pressures. The codes have specific chapters dedicated to the structural performance requirements for different materials: concrete, masonry, steel, wood. These aren't just guidelines. They are rigorous, legally binding requirements developed over decades, incorporating scientific understanding and lessons learned, all designed to prevent catastrophic failures and ensure structural integrity under expected conditions.
And fire safety must be absolutely paramount in the codes.
Oh, absolutely. It's literally a matter of life and death. The codes mandate specific fire resistance ratings for different building components: walls, floors, roofs, based on the building's type of construction and its use.
You mentioned type I, type 2 construction earlier.
Yes. The codes classify buildings into types based on the fire resistance of their structural elements. From type I, the most resistant, typically non-combustible materials like concrete and protected steel, down to type V, the least resistant, often unprotected wood frame. The required rating determines how long a component must withstand fire without collapse or allowing fire to pass through.
Okay.
And we talked about sprayed fire-resistant materials, SFRM, on steel members. That's critical because it insulates the steel, preventing it from reaching temperatures where it loses its strength. These measures are all designed to achieve two main goals. First, to compartmentalize a fire, slowing its spread through the building, and second, to ensure the structure remains stable long enough for occupants to evacuate safely. It's a fundamental layer of protection.
Speaking of evacuation, the design of egress paths ways out must be incredibly precise, too.
Extremely precise and highly regulated. The code meticulously defines what constitutes a means of egress and specific exits. This includes things like properly enclosed and protected interior exit stairways and ramps and exit passageways, essentially fire-rated corridors leading directly outside or to an exit stair.
Right.
What's particularly interesting, according to Building Codes Illustrated, is that once you are within a protected exit enclosure, like a stairwell, the distance one may travel is not limited by the code.
Really? So you could have a very long protected corridor.
Potentially, yes. The key is that you're in a safe, fire-protected path. This detail is actually critical in the design of complex buildings, especially high-rise buildings, because it allows for more flexible floor plan layouts while still ensuring everyone has a clear, protected route to safety.
That's clever. And finally, reflecting those broader societal values you mentioned, there's accessibility standards.
Yes, a truly crucial aspect of modern codes. In the U.S., the Americans with Disabilities Act, ADA, sets federal standards, and model codes like the International Building Code reference detailed technical standards like ICC A117.1. These ensure buildings are designed to be usable by people with a wide range of physical and sensory abilities.
So ramps, accessible restrooms, door widths?
All of that and much more. Clear floor spaces, reach ranges, signage, visual and audible alarms. It's comprehensive. What's especially significant, as Building Codes Illustrated notes, is that the ADA requirements may apply retroactively for existing buildings, particularly when alterations are made or in public accommodations.
So older buildings might need upgrades.
Often, yes. This really underscores society's deep commitment to ensuring that the built environment is equitable and usable for everyone, breaking down physical barriers and fostering true inclusion. It's about civil rights expressed through building codes.
Okay, we've covered the history, the design, the science of materials, the codes, but none of this happens without incredible coordination. Turning those plans and blueprints into actual standing functional realities requires immense foresight and management skill.
Oh, absolutely.
How do modern projects manage that incredibly complex dance of countless tasks, different teams, materials arriving, equipment? It really does feel like conducting a massive orchestra, but maybe with hard hats and often quite a bit of mud.
That's a great analogy. And what's truly insightful, I think, is how modern construction project management has evolved.
Right.
It's less about just listing tasks and more about understanding the project as an intricate system.
A system.
Yeah, almost like a biological nervous system. The core insight isn't just that we have better software now, but that every decision, every delay, every material choice, every team interaction creates ripple effects throughout the entire project. So the project manager becomes less of a simple taskmaster and more of a grand orchestrator of this dynamic living system. If you connect it to the bigger picture, It's all about understanding these complex interdependencies, proactively managing delays before they cascade, and ensuring predictable progress in what is inherently a very dynamic and often unpredictable environment.
So where does this formalized knowledge come from? Is there a standard approach?
There are definitely established frameworks. At the heart of much modern practice is the Project Management Body of Knowledge, or PMBOK guide, developed by the Project Management Institute.
Right, PMP certifications and all that.
Exactly. And our sources emphasize its focus on a systems view of value delivery. It's not just about completing the project on time and budget, but connecting the project's activities and outcomes back to advancing the client's overall organizational strategy, value, and business objectives.
So ensuring the project actually achieves what it was meant to achieve for the organization.
Precisely. It's that holistic view, making sure every action contributes to the bigger strategic picture, which is absolutely essential for large, complex projects to be truly successful in their ultimate purpose.
Okay, but before you can manage the system, you need to know what's in the system, right? The actual work, the materials. How does that happen?
That starts with meticulous estimating and quantity takeoff. Construction management describes quantity takeoff, sometimes called quantity surveying, as the precise process of measuring and counting everything needed for the project directly from the architectural and engineering drawings. How many cubic yards of concrete, how many linear feet of pipe, how many light fixtures.
That's painstaking.
It is. And the level of detail evolves. Early on in the conceptual or budgetary phase, you might do conceptual estimates based on historical data or square footage costs, just to get a rough order of magnitude for feasibility.
Ballpark figures.
Ballpark figures, exactly. But as the design progresses, you move to deterministic estimates, calculating detailed unit prices for every single item based on the final drawings. Now, what's really changing the game here, as detailed in the CMIA standards, Construction Management Association of America, are the 5D cost management capabilities within BIM building information modeling.
Okay, 5D. We heard about BIM earlier, the 3D model. What are 4D and 5D?
Great question. So 3D is a geometric model. 4D adds the dimension of time by linking the model elements to the project schedule. 5D adds the dimension of cost.
Ah, so every beam, every pipe in the model has a cost attached.
Exactly, and potentially a schedule activity. This means you can do dynamic quantity takeoff directly from the model, and it's incredibly accurate and updates automatically if the design changes. It allows for real-time, model-based budgeting and estimating. It's a huge leap in accuracy and efficiency for cost control.
Wow. Okay, so once you know the quantities and maybe the costs, the next massive piece is figuring out the timing, the sequence, scheduling methodologies.
Absolutely critical. The construction manager, or CM, typically leads this effort, establishing clear procedures for time management. This involves creating, constantly updating, and revising detailed project schedules, and often integrating them into a larger master schedule if it's part of a bigger program.
It's not just set and forget then.
Oh, definitely not. The CM continuously monitors actual progress against the plan, identifies any slippages or potential delays, and recommends revisions. The CMAA standards emphasize working collaboratively with all the contractors to get their input and ensure their commitment to the timeline. It's a constant iterative process of planning, executing, monitoring, and adjusting, like steering a large ship through constantly changing currents and weather.
And a core tool for this is the critical path method, CPM, right? I've heard of that.
Yes, CPM is fundamental to modern project scheduling.
Yeah.
Construction management breaks down the key concepts. It identifies the sequence of activities that determines the shortest possible project duration. That's the critical path. Activities on the critical path have zero float, or zero slack. Float is the maximum amount of time an activity can be delayed without delaying the entire project's completion date.
So if anything on the critical path slips, the whole project slips.
Exactly. Any delay to a critical activity immediately impacts the project's scheduled end date, unless you can somehow make up time later. Understanding the early start time, EST, and late finish time, LFT, for each activity defines the precise time window you have to perform that work. It highlights the absolute interconnectedness of all the tasks and where the real-time pressures lie. It's a powerful way to visualize and manage those dependencies.
But the real world isn't just abstract activities on a chart. What about things like weather? That must wreak havoc with schedules.
It certainly can. And good scheduling accounts for environmental factors. Construction project management explains how experienced schedulers can prepare specific weather-affected calendars for different types of work.
How does that work?
Well, you might assign certain activities based on their sensitivity to conditions. For instance, excavate abutment for a bridge might be possible in light rain or cold weather, maybe just slowed down. But an activity like exterior paint or pouring a finished concrete slab requires specific temperature ranges and dry conditions.
Right.
So the schedule can build in allowances for expected weather delays based on historical data for that location and time of year, or assign weather-sensitive tasks to periods when good weather is more likely. This kind of detailed planning anticipates real-world challenges and helps maintain realistic and achievable schedules rather than just crossing your fingers and hoping for perfect weather.
That makes sense. And finally, in terms of planning philosophy, there's this move towards lean construction and the last planner system, LPS. What's that about?
Lean construction draws principles from lean manufacturing, think Toyota production system, aiming to maximize value and minimize waste in the construction process. The last planner system, or LPS, is a specific methodology within lean construction focused on improving workflow reliability at the site level.
Okay, last planner. Who's that?
The last planners are typically the foreman or crew, leads the people actually assigning the work to the crews on a daily or weekly basis. LPS involves them directly in detailed short-term planning.
Ah, bottom-up planning.
Exactly. Research shows LPS aims to improve workflow reliability by increasing the match between what they plan to get done, the will, and what actually got done. It uses tools like collaborative weekly work plans with very well-defined, ready-to-go tasks,
Yeah.
look-ahead planning, usually 3-6 weeks out, to identify and remove constraints before they impact the work, and pull planning sessions where teams collaboratively map out the sequence of work for a specific phase, pulling work forward as prerequisites are completed.
So it's more collaborative and proactive.
Very much so. The goal is to reduce delays, improve coordination, minimize wasted effort, and boost predictability by empowering the frontline workers and fostering their commitment through direct involvement in the planning process. It's about creating a smoother, more reliable flow of work on site.
Okay, even with the absolute best planning, the most sophisticated schedules, the leanest processes, things still go wrong, don't they? No project ever seems to go perfectly according to plan.
It's putting it mildly.
So here's where it gets really interesting, maybe even stressful. How do project managers and the whole team handle the inevitable curveballs? Unexpected design changes, discovering something weird underground, materials not showing up, all while trying to maintain incredibly high standards of quality and safety. It truly feels like playing high-stakes chess, but the board and the rules keep changing mid-game.
That's a perfect analogy, and it raises that crucial question. How do you maintain control, maintain quality, maintain safety amidst constant change and inherent uncertainty? If we connect this to the bigger picture, it really comes down to a few key things. Having established clear, documented procedures for dealing with change, fostering strong, adaptable leadership that can navigate ambiguity, and building a project culture that emphasizes collaboration, communication, and critical thinking to proactively mitigate disruptions. It's the art of managing controlled chaos, always with a focus on solving problems effectively.
And our sources are really blunt about the inevitability of change in this industry, aren't they?
Absolutely. Construction Management Jumpstart states it very plainly. It is extremely rare to find a project that is built exactly as it was originally designed without any changes.
So it's not a sign of failure necessarily.
Not necessarily at all. Changes happen for all sorts of reasons. Genuine errors or omissions in the original design documents, nobody's perfect, discovering unforeseen site conditions, like hitting unexpected rock during excavation, or simply the client changing their mind or needing to adapt to new requirements. It's not a failure, it's a fundamental truth of the construction process that simply has to be anticipated and managed.
So how are they managed formally? You can't just change things on the fly, surely.
No, definitely not. When those changes inevitably occur and they affect the cost or the schedule, there's a formal, legally binding process involving change orders.
Right, the dreaded change order.
They can be contentious, certainly. A change order is the formal document used to add work to the contract or, in some cases, delete work from the contract. Crucially, it usually adjusts the contract price and/or the completion date, entitling contractors to extra compensation or time if the change increases the scope or complexity of their work.
And who manages that process?
The CMAA standards emphasize the construction managers, CM's lead role here. They administer specific documented procedures for initiating, reviewing, pricing, negotiating, and approving change orders, ensuring there's transparency, fairness, and proper documentation every step of the way. Good change order management is critical to avoid disputes later on.
Which highlights the need for contractual clarity right from the very beginning, I imagine.
Absolutely vital. A well-drafted contract anticipates potential issues. The project manager has a responsibility, as project management and construction points out, to proactively address any questionable items in the agreement long before they turn into problems on site.
Like
Yeah,
ambiguities.
exactly. Ambiguities, potential conflicts between drawings and specifications. And the contract needs to be clear on processes, like ensuring subcontractors adhere to the specifically called for products and materials in the specs. You can't just allow them to substitute something they claim is equal without a formal review and approval process, because that can lead to disputes about quality or performance down the line. Construction law even adds a cautionary note about vague terms. It points out that using a phrase like turnkey contract isn't necessarily a term of art with a fixed legal meaning, and it might not automatically guarantee the efficacy of the works, meaning it doesn't guarantee the finished project will actually perform as intended. Precision and clarity in the contract documents are paramount to manage expectations and define responsibilities clearly.
But even with clear contracts and change orders, disputes can still happen. Claims must arise sometimes.
They do. So effective claims management is another critical function for the project manager or CM. The goal isn't just to react to claims, but to proactively manage the risk of claims. The CM establishes methods and procedures to minimize the impact of claims through things like meticulous record keeping, clear communication protocols, and aiming for prompt and equitable resolution of issues before they escalate into formal claims.
Trying to nip problems in the bud.
Exactly. The CMAA standards even recommend that all claims and potential claims should be discussed weekly at the progress meetings. This fosters proactive communication and collaborative problem solving, trying to address disagreements or potential extra costs early and fairly, rather than letting them fester and potentially end up in costly legal battles.
Okay, so that's managing changes and disputes. But underlying all of this is the constant, non-negotiable focus on quality and safety, right?
Absolutely non-negotiable. These are paramount responsibilities. The CM plays a key role in monitoring contractor compliance with the quality level expected, often through regular site inspections, reviewing work procedures, and coordinating essential field testing of materials like concrete strength tests and installations like pressure testing pipes.
Making sure it's built right.
Making sure it's built according to the plans and specifications and meets the required standards. And on safety, the CMAA standards stress the importance of owner commitment to establishing comprehensive overall safety programs that go beyond just basic regulatory compliance. The CM has a responsibility to monitor the site for hazards, ensure contractors are following safety rules, and crucially, in imminent danger situations, they are empowered and ethically obligated to suspend the relevant work immediately to protect workers.
That's a huge responsibility.
It is. It underscores the profound ethical, legal, and practical responsibilities involved in construction management, where people's lives and well-being are literally at stake every single day.
And pulling all these threads together, managing changes, risks, quality, safety, surely requires strong leadership and motivation, not just ticking boxes.
Absolutely fundamental. Processes and procedures are essential, but they don't work without effective leadership and a motivated team. The PMBOK guide makes this very clear. Project teams can thrive when project team members use appropriate leadership traits. This isn't just about the project manager. It's about fostering leadership at all levels.
Okay.
And understanding what truly motivates people on the project. Is it financial incentives, public recognition for good work, having autonomy in how they do their job, feeling a sense of purpose in the project's outcome, or opportunities for professional growth? Recognizing and tapping into these different motivators helps foster a sense of shared responsibility towards achieving the project goals together. Effective project management isn't just about the technical side. It's fundamentally about inspiring, empowering, and enabling diverse groups of people to work together effectively, collaboratively, and safely towards a common vision, often under very challenging circumstances.
We've talked a lot about the complexities of managing construction traditionally, but technology is racing ahead. What about the future? How is the digital revolution fundamentally changing not just what we build, perhaps, but how we plan, design, coordinate, and manage the entire process? It really feels like we're on the verge of, or maybe in the middle of, a massive transformation.
I think that's absolutely right. We're definitely in the midst of it. And what's truly fascinating here is how digital tools, particularly BIM, are transforming construction. It's moving away from what was often a reactive process, discovering problems on site and then figuring out how to fix them, towards one that is highly predictive, highly integrated, and incredibly collaborative.
So catching problems earlier.
Way earlier. often before they even leave the digital realm. This isn't just simple automation of old tasks. Sources like the BIM Handbook describe it as a profound paradigm change, an epical transition in design practice. It's fundamentally redefining how project information is created, shared, and utilized, and how decisions get made across every single phase of a project's lifecycle, from the earliest concept right through to operations and maintenance. It's a significant leap forward in both managing complexity and achieving better control.
Okay, so let's really unpack BIM as a paradigm shift. You mentioned it's different from older CAD systems.
Fundamentally different. CAD, or computer-aided design and drafting, was essentially just using computers to do electronic versions of traditional 2D drawings.
Hmm.
It was faster, maybe easier to revise, but the underlying process wasn't that different. BIM, as Construction Management Jumpstart explains, is a database-driven modeling system designed for collaboration. The key is the I in BIM information. You're not just drawing lines and shapes, you're creating intelligent 3D objects. Walls, doors, pipes, beams, and each element within the BIM file comes with information attached.
What kind of information?
All sorts. It's not just the geometry, size, and shape. It can include construction details, performance characteristics like thermal resistance for a wall, product specifications, manufacturer model number, cost data, phasing information, even maintenance schedules. It's a rich, interconnected digital database that represents the building, not just draws it. It's a living digital twin.
Okay, that sounds powerful. What are the core benefits that everyone talks about with BIM?
There are several huge ones. The BIM handbook highlights that BIM automates spatial interference checking. That's usually called clash detection.
Finding where things collide.
Exactly. The software can automatically analyze a 3D model, often combining models from different disciplines,
Hmm.
structural, mechanical, electrical, plumbing, and identify places where, say, a large air duct is trying to occupy the same space as a major structural beam.
Which would be a nightmare to discover during construction.
A costly nightmare involving delays and rework. Finding these clashes digitally before construction begins saves enormous amounts of time and money. That's a massive benefit right there.
Okay, what else?
Another core benefit is that BIM guarantees consistency across all drawings and reports. Because all the drawings, plans, sections, elevations, schedules are generated directly from the central 3D model database. If you change an element in one view, it automatically updates everywhere else.
So no more coordination errors between different drawings.
It virtually eliminates that entire category of errors, which were historically a major source of problems caused by using out-of-date plans or manual updates being missed. And perhaps most visibly, BIM vastly enhances visualization and communication at all scales and phases. Everyone involved, the client, the architects, the engineers, the contractors, even the subcontractors, can explore the 3D model, understand the design intent, see how complex areas go together long before breaking ground. It's an incredibly powerful communication tool.
So clash detection, consistency, visualization. Are there more advanced BIM capabilities too? You mentioned 4D and 5D earlier.
Yes, the capabilities go much further. We talked about clash detection, its ability to check for interferences by searching for intersecting volumes, often combining multiple models from disparate sources. That's huge.
Right.
Then there are 4D schedules. This is where you dynamically link the activities from the project CPM schedule to the 3D objects in the BIM model.
So you can watch the building get built on screen.
Exactly. It creates this graphically rich and animated representation of the planned construction sequence set against time. You can literally watch a simulation of the construction process week by week or even day by day. It's incredibly powerful for phasing, coordinating, and communicating planned work, especially for complex sequences or tight sites. It makes the schedule instantly understandable to everyone.
That sounds amazing for planning and 5D cost management.
That's adding the cost dimension. As the CMA standards describe, every element in the BIM model can be attributed to what it will actually represent in terms of resources and respective costs. So that wall object knows not just its dimensions, but potentially the cost of the studs, the drywall, the insulation, the paint, and the labor to install it.
Oh.
This isn't just a static spreadsheet linked somewhere. It enables parametric and dynamic quantity takeoff directly from the model for incredibly accurate, real-time cost estimates. It also facilitates model-based budgeting and estimating, which is fantastic for value engineering. You can explore different design options in the model and immediately see their cost implications, helping optimize the design for budget throughout the process.
And does this impact the actual physical construction too, the fabrication?
Massively. The BIM handbook notes how BIM is making traditional paper drawings largely disappear for many fabricators, especially in steel and precast concrete. Instead, data from the BIM model is fed directly into CNC machines, computer numerical control, for automated cutting and drilling, or used with laser technology for precise layout and assembly in the workshop.
So direct digital fabrication?
Exactly. They even mention using color-coded 3D models on tablets in the field to help workers visualize and assemble incredibly complex components, like intricate reinforcing steel rebar cages. This direct integration of design data into the fabrication and assembly processes significantly increases precision, reduces errors, and boosts efficiency both in the factory and out on the site.
With all this complex digital information flying around, managing it must be a challenge. Has that created new roles?
It certainly has. With multiple teams contributing to and using the BIM model, maintaining data integrity is crucial. CMAA standards discuss the emergence of the BIM integrator role, or similar titles like BIM manager or coordinator. This person is responsible for establishing and enforcing protocols for model development, ensuring proper document control, managing access rights, coordinating model sharing between different disciplines, and basically acting as the guardian of the central digital twin, especially in complex project delivery methods where collaboration is key.
Makes sense. You need someone in charge of the master model.
Absolutely. And all of this, the intelligent modeling, the integration, the direct link to fabrication, is leading towards something potentially revolutionary, what some commentators, like those in the City of Tomorrow, are calling a third industrial revolution, enabled by digital tools. They connect BIM and digital fabrication to the concept of mass customization.
Mass customization. Isn't that an oxymoron?
It sounds like it, but the idea is that with digital design and automated fabrication, there is effectively no difference in cost or complexity between creating identical versus unique objects.
Right.
Think about 3D printing, for example. It takes the machine the same effort to print 100 identical items as it does to print 100 slightly different items, because the complexity is handled by the software, not by retooling a physical assembly line. This means items can potentially be manufactured for about the same cost, whether you need thousands of identical components or a single bespoke, uniquely designed unit. It fundamentally shifts the paradigm away from mass production towards individual control, adaptation, and tailoring in the built environment. It opens up incredible possibilities for highly customized, yet still efficient construction in the future.
Okay, we've explored the grand sweep of design history, the intricate science of materials, the complex orchestration of huge projects, the digital revolution. But underpinning all of this, always, are the people. The individuals making the decisions, having the ideas, doing the work.
Mhm. The human element.
Exactly. What's the unique contribution, the essential role of the engineer, the architect, the skilled craftsperson in actually shaping our world?
It feels like it goes beyond just the technical skills. It's about the human spirit, the intellect, the values they bring to the process.
That's a critical point, and maybe the most important one. It really raises the question, what defines the true value of engineering and architecture beyond the technical calculations or the aesthetic flourishes? If we connect this to the bigger picture, I think it's about balancing that undeniable technical prowess with a profound sense of ethical responsibility, a clear forward-looking vision, and often a deep, almost intuitive understanding of materials and, crucially, of human needs and experiences. It's this powerful blend of intellect, creativity, intuition, and ethical consideration.
And our sources really touch on that ethical dimension, the idea of an engineering conscience. Yes, significantly. The existential pleasures of engineering, for example, highlights this call for engineers to develop and exercise a conscience. Especially now, in the wake of growing environmental concerns and social crises, there is a call for engineers not just to solve technical problems, but to give warning and refuse to work on evil projects.
That's a strong statement. Evil projects.
It is strong. It raises profound ethical challenges about the ends to which engineering skills are applied. And navigating those pressures can be incredibly difficult. We see a stark example in the power broker's description of the fiercely independent engineer Ole Singstad, who worked on New York's tunnels.
Right.
The book notes how Singstad apparently despised Moses' aides, Robert Moses, the powerful public works builder, because he felt they were subordinating their own objective views of an engineering problem to tell the Triborough chairman Moses what he wanted to hear.
Wow. Resisting political pressure.
Exactly. It's a powerful reminder that professional integrity, sticking to objective analysis, even when it's unpopular, is absolutely paramount. Especially when faced with immense political or economic pressure, the stakes are often incredibly high.
And that integrity, that vision, extends into the role of the architect as visionary and engineer too, doesn't it? We heard Le Corbusier's view earlier.
We did. Le Corbusier famously reiterated that the architect is above all an engineer, but he also emphasized that the plan proceeds from within to without. That means the design should flow logically from the building's internal function, its purpose, its core idea, outwards to its external form. He even viewed a building as an organism comparable to a living being.
A holistic view.
A very holistic perspective. Seeing a building not just as an object but as a dynamic functioning entity requires not only technical mastery, but also that profound imaginative capacity, that vision. And you see the excitement of that in figures like Louis Sullivan, the great American architect. His autobiography details the joy of discovery he felt, finding congenial coworkers, and getting the opportunity to take his own responsibility on major projects like the Borden Block or Large Theater in Chicago. It highlights the architect's crucial role in shaping not just individual structures, but the character and experience of the broader urban landscape.
And complementing that high-level design and engineering vision, there's this immense, almost foundational value in the value of craft and understanding materials at a really deep level.
Absolutely essential. It grounds everything else. Kidder, writing about house framing, reminds us that the treeness of lumber, its grain, its knots, how it behaves, is a salient fact for good framers. It emphasizes that deep, intuitive, hands-on understanding required to work with materials effectively, knowing their inherent strengths, their weaknesses, their tendencies.
You can't just learn that from a book entirely.
Not entirely, no.
Yeah.
And Matthew Crawford in Chop Class, as Soulcraft, draws this really powerful analogy. He suggests that a good repairman, by diagnosing and fixing things, develops a more solid sort of command based on real understanding.
Oh,
Why?
okay.
Because they have to get outside their own head and noticing things objectively to figure out what's wrong and how to fix it.
Right.
He argues this process chastens the easy fantasy of mastery, suggesting that true expertise, true understanding, comes from that direct, often challenging engagement with the physical world, coupled with a humble respect for the materials and systems themselves. This deep, hands-on knowledge, this craft sensibility, is what grounds all the high-level design and complex engineering, making it tangible, making it real.
So we've looked at the roles, the responsibilities, the vision of the individuals involved. But let's zoom out again. Here's where it gets really interesting, I think. How do these monumental structures, these intricate systems, these design choices, actually impact our daily lives, our communities, the very fabric of our cities? Often in ways we don't even consciously notice. It feels like this constant, often invisible negotiation between the things we build and how we end up living.
That's a perfect way to put it. What's truly fascinating here is that profound, often unnoticed feedback loop between our constructions, our buildings, our infrastructure, and our societal development. If we connect this to the bigger picture, it's all about how physical spaces actively shape human interaction, economic vitality, social equity, and the very nature and quality of urban life. Our buildings aren't just passive backdrops, they're active participants, influencing our behavior, our opportunities, our sense of community in countless, often subtle ways.
And sometimes, unfortunately, that impact can be quite negative, can't it? We see examples of urban transformation and its consequences that didn't work out well.
Sadly, yes. Kostoff discusses how some implementations of modernist solutions for housing and urbanism, ideas that might have seemed rational or efficient on paper, sometimes led to clear-cut land, the imposition of isolated commercial towers separated from housing, and ultimately fragmented cities lacking cohesion and human scale.
Like Pruitt-Ego in St. Louis, maybe?
That's a classic tragic example often cited. In the worst cases, these environments could become dysfunctional, even dangerous, described sometimes as battlefields of crime and vandalism. It's a stark reminder of how even well-intentioned planning, when implemented without a deep understanding of social dynamics and human needs, can have devastating unintended consequences, fundamentally altering the fabric of communities for the worse.
Which brings us to someone who thought deeply about how cities actually work on the ground. Jane Jacobs.
Ah, yes, St. Jane to many urbanists. Her observations on the dynamics of urban spaces were groundbreaking. She famously contrasted the vibrant success of Rittenhouse Square in Philadelphia with the decline of nearby Franklin Square. Her point was that cities generate diversity, safety, and economic vitality only when their districts form economic pools of use, meaning they have a healthy mix of different activities, buildings of different ages and conditions, and attract different people at different times of day for different purposes.
That intricate urban ballet she described.
Exactly. And her critique of big city government often being just stretched little city government also resonates. She argued that simply scaling up administrative structures designed for smaller towns often fails to address the inherently different, more complex operational problems and social dynamics of large, diverse metropolises. Her work is a timeless lesson in observing and understanding the organic, often messy, but vital complexity of real urban life, as opposed to relying solely on abstract, top-down planning theories. But infrastructure, when done right, can also be incredibly visionary and transformative in a positive way, literally connecting the world and enabling progress. Think of someone like visionary infrastructure builder Isambard Kingdom Burnell.
An absolute giant of engineering.
Oh.
Roth's biography describes his expansive vision, which really transcended national borders. He didn't just build iconic railways like the Great Western Railway across England.
Connecting London to Bristol.
Yes, but he didn't stop there. He immediately started thinking about the next step, designing and building massive iron steamships like the Great Western, the Great Britain, the Great Eastern, to continue that journey across the Atlantic, effectively connecting his railway terminus in Bristol all the way to New York.
That's incredible systems thinking for the 1830s and 40s.
Astonishing.
Mm-hmm.
His ambition was so grand, in fact, that the port of Bristol itself struggled to adapt its harbor facilities quickly enough to accommodate his revolutionary ships, which were consistently the largest and finest ships in the world at the time. It's a powerful example of how visionary infrastructure can both enable incredible progress and simultaneously challenge existing systems and cities to evolve rapidly or risk being left behind.
And looking ahead now, we're entering an era of potentially even more integrated infrastructure with the connected city.
The smart city concept.
Right. The City of Tomorrow explores ideas around ubiquitous computing and smart cities, where vast networks comprising thousands or millions of sensors embedded throughout the urban environment continuously collect data on everything from traffic flow and energy use to air quality and noise levels.
Okay.
And this data can then be used to control network-enabled actuators that dynamically transform space. Think adaptive traffic lights, responsive building systems, personalized information displays, so the city itself becomes intelligent.
That's the vision. The book suggests this creates phenomena like ambient intimacy, a sense of connection facilitated by technology, and contributes to a feeling of a global village, where technology recedes into the background but fundamentally reshapes human connection and the experience of urban life. The city itself potentially becomes this intelligent, responsive system, constantly learning and adapting. Of course, this also raises huge questions about data privacy, surveillance, equity, and control, but the technological potential to reshape urban experience is profound.
Wow. We have covered an incredible amount of ground, haven't we? From ancient Egyptian geometry to networked smart cities, through materials science, project management chaos, ethical dilemmas.
It's a vast territory.
It really is. So, pulling it all together, what does this all mean for how we should approach building, managing, and living in our built environment in the future? What's the biggest, most enduring lesson we can take away from this deep dive into this incredibly complex world?
That's the key question, isn't it? If I had to distill it down, connecting it all back to the bigger picture, I'd say the profound and multifaceted impact of our built environment demands, more than anything else, a true systems perspective.
Systems thinking.
Exactly. This means actively looking for and understanding the interconnectedness between different parts, recognizing the influence of feedback loops, both positive and negative, anticipating delays, and being constantly aware of the potential for unintended consequences. It's about designing and managing for the whole system, not just optimizing individual components in isolation. And critically, it's about building in adaptability and learning, aiming for true resilience in the face of inevitable change and uncertainty.
And thinking in systems, the book by Donella Meadows really hammers home the importance of interconnections, doesn't it?
It does, brilliantly. It emphasizes that critical point. It's often easier to learn about a system's elements than about its interconnections. We can easily list the parts of university departments, students, buildings, but the real dynamics lie in the interconnections. The flow of information, including gossip, the allocation of budgets, the communication of knowledge, the power structures. In the built environment, this means seeing how a specific material choice connects to global supply chains and embodied energy, how a particular urban design connects to long-term social equity or public health outcomes, how an engineering decision connects to decades of future maintenance costs and adaptability. It's recognizing that it's all fundamentally intertwined.
And within these complex interconnected systems, feedback loops and delays play a huge role in how they behave over time.
Absolutely pervasive and powerful. Meadows explains how feedback loop cycles, where the output of an action influences future actions, are what cause system stocks, like the amount of energy consumed, the level of resources available, the number of buildings in good repair, to maintain stability, to grow, or to decline over time. And delays, too, are pervasive in systems and can be incredibly strong determinants of behavior. Think about the delay between investing in energy efficiency measures and seeing the actual reduction in energy bills, or the delay between building new housing and seeing an impact on affordability. Meadows stresses that changing the length of a delay may make a large change in the behavior of a system. Understanding these dynamics, the loops and the lags, allows us to better anticipate how systems will behave, identify potential leverage points for effective intervention, and hopefully avoid policies that create destabilizing oscillations or overshoot critical limits. It's about managing the dynamics, not just the static parts.
This system perspective also leads to insights about individual actions versus overall system performance through concepts like bounded rationality and system redesign.
Yes, that's another key concept from thinking in systems. Bounded rationality basically means that individuals or organizations make decisions that are perfectly rational from their own limited perspective, based on the information and incentives they face.
Makes sense.
But those individually rational decisions might not serve the welfare of the system as a whole. Think of developers choosing cheaper, less energy-efficient building components to maximize short-term profit, even if it leads to higher long-term energy costs for occupants and society. This insight highlights why simply blaming or replacing individual actors often doesn't fix systemic problems. Instead, it points to the critical need for redesigning the system itself, changing the rules, the incentives, the information flows, the goals to improve overall performance. It's about fixing the game, not just yelling at the players.
Which really brings us full circle, suggesting that nothing is ever truly finished or perfect. It points towards continuous improvement as an ongoing necessity.
Precisely. Peter Drucker, in Management Tasks, Responsibilities, Practices, makes this crucial point. Effectiveness was obtained for a time, but not forever. Solutions that worked in the past might become ineffective or even counterproductive as conditions change. This stresses the inherent need for what he called planned obsolescence and planned abandonment, not just of physical things, but of outdated policies, procedures, and ways of thinking.
So always questioning, always adapting.
Exactly. It requires a constant process of ongoing improvement, a concept also central to Eli Goldrat's quas, the goal and the theory of constraints. The built environment, like any complex system, is not a static achievement to be completed and then admired. It's a living, evolving entity that requires constant attention, adaptation, learning from feedback, and an unwavering commitment to progress if it's going to truly serve human needs and societal goals effectively and sustainably over the long term. #outro.
Well, what a journey. We've really traveled through millennia of building, haven't we? From the almost spiritually charged stone structures of ancient Egypt, right through Roman pragmatism, Gothic ingenuity, Renaissance reinterpretations, modernist revolutions, and now into the complex digital models and interconnected systems of tomorrow's potential smart cities. We've seen how every single beam, every wall, every design choice, every management decision really is a testament to human ingenuity, to our evolving technology, and to that incredibly complex, sometimes messy coordination required to make it all happen.
It really underscores that our built environment is this truly dynamic, almost living system. It's constantly being shaped by that intricate interplay between deep technical expertise, sophisticated management principles, evolving technologies, and fundamentally, our deepest societal needs and values. The powerful lessons from all these diverse sources, I think, remind us that to build well, to build responsibly, effectively, beautifully requires understanding not just materials and methods, but also understanding people, understanding systems, and understanding how they all profoundly influence one another to create the world around us.
That's beautifully put. So perhaps a final thought for you, our listener. The next time you walk through a bustling city square, or maybe glance up at a soaring skyscraper, or even just pause to consider the structure, the comfort, the efficiency of your own home, take a moment. Reflect maybe on those invisible layers upon layers of history, science, human effort, collaboration, and ingenious problem solving that had to converge over time to create that very place. And then perhaps consider this. What responsibility do we all share as both the inhabitants and the ongoing innovators within this built world in consciously, thoughtfully, and ethically shaping its next vital evolution?